Hello everyone. So in today's video we're gonna see how to set up a metallurgical simulation in Codaster. Okay, so what we are going to do today is to try to replicate a Jominy quenching test. Okay, so the first thing to do is to go to the geometry module, and in this module we're gonna create the geometry of the Jominy quenching test. So we're going to simplify things a little bit and assume that our problem is fully represented by a cylinder of a length of 100 millimeter and with a diameter of 25 millimeters. Okay, so to create this geometry in the module, it's really easy. We just have to create a new entity, primitive, cylinder. Let's name cylinder sample. Okay, so we will be working with meters and the radius it's 0.0125 and the 8 will be 0.1. Apply and close. So now the current view is way too big for the cylinder, so we'll have to fit the view, and here it is, our cylinder. So now we can create the groups to apply boundary conditions later on. Okay, so we go to new entity, group, create group. We're going to create the first group for the face that will receive the spray quenching. We'll name it quenched face. We select the main shape. We select the upper face, add, apply. We then select every other faces, and we are going to say that in our case they are subject to an air cooling. Okay, so and we remove the previous face and we name the group air cooled, apply and close. Okay, so now we should have our groups. Okay, so yes, we have our groups. That's it for the geometry creation. I'm gonna save the study. So let's name it. Let's create a folder video. Name it, I don't know, Jominy. Save. Okay, that was it for the geometry creation. Now we can go to the mesh module, and we are not going, again we have to fit the view and display the sample, the geometry better. It will work now. Okay, so we are not going to make a complex mesh. The point of this video is to set up a functioning metallurgical simulation. So we're going to create the mesh real quick. We go to mesh, create mesh, geometry. We select our geometry sample, mesh type, let's keep any, NaGen 1D, 2D, 3D, and for the hypothesis, let's just put that, and well, let's keep that. Okay, so apply and close. Now we have to compute the mesh, but by default you will see that the group of faces have automatically been imported. So let's compute the mesh, and that's it. Okay, so if I hide the geometry, we can see our mesh. Obviously it's way too coarse. The mesh is not really accurate, but for what we're trying to show in this video, it's gonna be okay. So we can start to set up the study in Aster Study. Aster Study is the Codaster GUI embedded to the Salome Mecha platform. That's where we can set up the case. Okay, so we first have to create a stage, add stage, and let's name it quenching. Good. First thing first, we have to import the mesh using the command lire maillage, which means in French read a mesh. Okay, so we only have one mesh in this study, and we apply. Okay, that's it. We can save. Now we can define the model of the simulation, and in Codaster, to set up a metallurgical simulation, we have to create a thermal simulation, because metallurgical simulations, metallurgical results will be directly deduced from the thermal analysis. Okay, so we're going to affect one model over everywhere, since we only have one material meshed geometry. Okay, so, and the phenomenon will be thermic or thermal. And the modelization will be 3D diag. I let you check the documentation about the diagonalization of the thermal mass matrix to see why we need this modelization, but it relates to how Codaster manages the thermal shock. Okay. Apply. That was it for the model. I'll save the study. Now let's create, it would be, let's create the material. We're gonna need two things. The first one will be a CCT diagram. In Codaster they are named TRC, and they are built with the operator defeat TRC. Okay, so the thing is that it's quite complex to create a metallurgical file, a metallurgical material file in Codaster. It will be too long to explain it in this video, so I'm just going to use an already existing material file imported from a Codaster test case. Okay, so I'll keep it empty for now. There will be some error messages, but that's fine. We will correct that later on. I'm saving the TRC. Okay, now we need to define a material using the operator define material. Sorry, my computer is a bit slow. Yeah, we're gonna need three things. The first one will be there, which is where we define the thermophysical properties of the steel, such as the thermal conductivity. Meta acier, which means meta steel, where we will be defining the metallurgical properties of the steel, and then dirt meta, where we'll define the hardness of the different phases. Okay, so let's apply. Again, we will have some error messages, but that's fine. Okay, so now we're going to import material data. To do so, I have another window of Codaster of Salome Mecha open, and I'm going to go to the Aster Study module. Okay, so I will use an already existing test case made by EDF. It's really useful. So I'm going to import a metallurgical test case, which is named MTLP 100, if I remember correctly. Okay, yes, we can see the whole architecture of the case. That's extremely useful when you are stuck in a simulation, don't know what is going wrong. Comparing your case with a test case might solve your problem. Okay, so but now we want to grab the material data. So to do so, we are gonna click on the defined CCT diagram, and we're going to go to the text mode, and we're going to copy the defined CCT diagram into our case. Okay, so and now we can go to the text mode and overwrite everything, apply, and that's it. You can see that now the CCT diagram turned black, which means that it has everything required for its definition. Okay, so we can close that. And we are going to do the same with for the defi material operator. Okay, so going back to the test case, and we're waiting. Okay, so we go back to text mode, and we can see that we have here the definition of the different phases. Here the informations regarding the metallurgy of the steel, and there the thermophysical properties of the steel. Okay, so we're going to copy all of that into our case. We're going back to the text mode, applying everything, close, that's it. I'm saving this case. Okay, so now we have to affect the material created to the mesh, to this mesh. Okay, so we'll be using the operator affect material, and we only have one mesh, and we're going to affect we only have one material in this case, so it's quite straightforward. Okay, apply, that's it. I'm going to save the study. Okay, so now we need to create two lists. Let's say that in this case we want to simulate 1 minute of quenching, 60 seconds of cooling. So we will need to create one list to define the time step, where will be the time at which the case will be calculated, and then another list to define at which time the results shall be saved. Okay, so we're going to do so. To do that using this command, defi list réel. We're going to start, we want it to start at 0, and we can define it with an interval. Okay, so we want to simulate up to 60 seconds, and in how many steps? I'm going to put 240, but again, the purpose of this video is not to teach how to have the correct time step. That you'll have to figure it out by yourself. So let's just put that for now, and hopefully it will work. Okay, so apply. Okay. I'm going to rename that list time. Save the study, and I'm going to create another list, but this time it's gonna start at 0, until 60, and let's say that we only want 20 results, because in Codaster by default, if you do not specify when to save your results, every increments will be saved and your result folder will be huge. Okay, so that's why we need to do so. Okay, apply. That's it for the list. Okay, so I'm going to rename it list result. Save. Okay, so now for the boundary conditions, we're going to affect thermal type of boundary conditions. We're going to impose an exchange. We're going to make it overly simplified and simply define different heat transfer coefficients on the different phases. To simplify, these coefficients will be constant, but then again, in reality, they will vary with temperature. Okay, so let's see. No, we want to apply it over the groups that we created. If we want to simulate, if we want one condition for the quenched phase and another condition for the air-cooled phases. Okay, so we're going to define a fast cooling on this phase. Let's say that 5,000 watt per square meter Kelvin, and for the temperature associated, 20 degrees. We're going to define another exchange, this time on the air-cooled phases, okay, with a heat transfer coefficient of 10 and an external temperature of 20. Apply. Okay. Okay, so now we have to create the analysis, the thermal analysis. So we need to create a linear thermal analysis. The model, we only have one model, we only have one material field. Excite, it's the boundary conditions, the loads. We only have one thermal load, that's it. Since we want it to be transient, we need to specify an initial temperature. It's in eta ini, or initial state, and let's say that we'll start the simulation at 900 degrees. Okay, that's it. Apply. We'll keep the solver option by default. Okay, so apply. Okay. Now we need to initialize the metallurgical fields. We'll have to say at the beginning of the simulation how much of each phases we have. Okay, so to do so, we are going to create a new field. Let's name it ini phase for the initial phases. I let you see Codaster documentation to see why we are choosing this type of field. It will be this one, cart var2 air, and the operation we will want to affect it over our mesh. And now, yes, we're going to want to apply it everywhere because we only have one geometry with homogeneous with a completely defined phases definition. Okay, so again we'll have to define 7 new fields. Okay, um, the five first one are for the phases, to define how much of each phases you are. The first one is the ferrite, the second one the pearlite, the third one the benite, the fourth one the martensite, the fifth one it's the austenite. And in a Jominy quenching test, since we are starting with a purely austenitic structure. We won't use that field. If I remember correctly, it's related to the martensite temperature or something like that, but I never used that field. And the last one we have to precise, it's for the grain size. Again, I'll put in the description of the video every relevant documentation for this kind of cases where everything will be explained more deeply. Okay, so and we're gonna need to name our fields this way. So we're going to have to name the ferrite V1, the pearlite V2, V3, etc. V4, V5, V6, V7. Okay, so now we apply and we can set up the methodological analysis. To do so, we're going to the pre-analysis tab. I don't know why it is in there in pre-analysis, because what Codaster will do is that it will compute the thermal history of the billet of the cylinder and post-process these thermal results accordingly to the CCT diagram to deduce the metallurgical phases at each time step. So it's doing a metallurgical post-processing of the thermal analysis. We go to Calc Meta and we want to apply the metallurgical calculation to our thermal analysis. That's good. The option, we want to compute every metallurgical fields. Methyl no, methanol no, butyl no, dirt no. The initial state will be the one defined in the creation operator, ini phase. Okay, and the behavior will be the metallurgical model associated to steel. It's the vehicle model, okay. But it's already defined by default. Apply. Okay. You can save the study. I forgot in analysis to define the time steps. So the increment will be the first list for the time. Sorry. Apply. Okay. Now for the post-processing, we'll need two things. The first one will be the extraction of the results for the previously specified time step. Okay, so we want to extract the result residue of our thermal analysis, and that is called an archivage, to select only some results, and there we can specify which time step we want to save, and this time we choose the second list, the list for the results. Okay, we apply, and then we want to print out our results. To do so, we will be using the impr resu operator, and we'll have to create the the result folder. Let's say let's call that results, and name that results also. Okay, so we want the results of our mesh, and we let the other options by default. Apply. I think that's it. I think we are done with the setup. So I'm saving the case one last time. To launch the case, we go to the history view. We add our current case. We can set the auto refresh to every 5 seconds, because our case shouldn't be too long to compute, and we can launch the case. Okay, so actually it won't be too long, but then again my computer is quite slow and it will work. But if it takes a lot of time, I'll simply cut the recording of the video, and we will see later on for the post-processing. So we are almost there. Okay, so it's done and it seemed to have worked. Okay, so to see the result, we do a right click over the result file with the point made extension, and we go to post process. Okay, so we have an error message. Why don't we have any results? Why don't we have any? We don't have any results, yet it computed what we wanted to compute. We don't have any. We don't have any warning, so that it's quite strange. Case view, output. Okay. Okay, I forgot. Okay, so my bad. We should not have had selected the mesh. We should have had selected the results. Okay, so and thankfully nothing was calculated because it was still on the thermal analysis. We might have had 240 results. So we want to select for the result this field, resultat, and our result extraction. Okay, so sorry, my bad. This time we can delete these results, and current case we can we can add our case and run it again. So there wasn't any kind of error messages, so obviously it will work again, but this time we will have our results. So as we've seen before, it didn't take so many time to run, and I think I will just wait for the simulation to end. We are okay, so we are almost halfway there. Fresh. Yes, it's going to be quick. And that's almost it. Okay, so it seemed to work. This time, hopefully, we'll have results. Yes, this time we have results. And as you can see, with only 20 results, it's already 40 megabytes. Okay, so we can check that the temperature is coherent, that there is no oscillation. So at the second time step, it's okay. So it seems quite coherent, like if we did not choose the 3D diagonalization, we could have had temperature oscillation and first heating in some part of the billet. Okay, so it seems okay. And we can see the methodological fields there. I advise you to use this field, nommé, because there you can see that we have the real name of the phases and not V1, V2, V3. And if we want to display the martensite, we've done a fast quenching, so we should have martensite. Yes, we can see that martensite is formed, and we should be almost fully martensitic at the top of the cylinder at the end of the simulation. Okay, so yes, almost. The remaining should be benite. Okay, so no, I think it still hasn't finished to transform, but our result seems coherent, and we can check the hardness. Okay, so it seems quite, it might be a little soft for the martensite. I don't remember the carbon percentage, but in the material file. But the important thing to notice is that our case seems to work, and that was it for today. Hopefully it has been interesting and you've learned something, and see you next time.